Okay, so we are going to begin with this new chapter on stress. This is my favorite chapter. Okay, not because I love to have stress, but it is very mathematical in nature, and I love to do these things as well as the next chapter, strain. So, stress and strain, I love it. The other reason is that these two chapters are absolutely fundamental. So some of you may argue that if it is so very fundamental, should this have been the first two chapters? Yes, in certain cases, it does make sense to start with these two chapters as a thing. But the problem is that uh, sometimes, if you just start like this at the second year level, where it is just maths, uh, you don't get a feel of the engineering thing, which is why at the second year level we have tried to do this. That first we present the various specific cases like torsion, bending, deflection, buckling, all these things. Now we are going to bring everything together on this common ground of stresses and strains. And finally, we'll bring back everything together, all these fundamentals together with the applications in the next chapter, or not in the next chapter, the next to next chapter on combined loading. Okay, as the name suggests, everything will be together all the time. Okay, so we'll do the stress chapter, and there's a lot of ground to cover. So we'll have to be like on our toes, and like we'll have to take a little bit of stress to cover this chapter also. Okay, but no matter. And those of you who are a little bit mathematically inclined, I think you will absolutely love it. Okay, so uh, I will not ask what do you mean by stress. Okay, I will not ask you anything. Rather, what I will do is I will start with a concept which some of you may have heard, depending on how you were taught in your basic engineering mechanics. I will not assume any prior knowledge. Okay, I'll start from the absolute basics. The concept is called traction. Okay, have you heard of it? ठीक है. Even if you have not heard of it, then also ठीक है. Okay, some of you who are fans of Formula 1, if you hear the commentary, then you will probably you would have probably heard from the commentary that the tires are not getting enough traction on a rainy day, something like that. Okay, that has connection with this, but what they mean is in a very general colloquial sense of the grip. Okay, the grip of the tires, that also has, I mean, is a meaning which is subsumed within this general mathematical definition of traction. But now when I'm going to define traction, you keep your mind absolutely free and open, forget everything that you have learned, everything including the previous chapters. Okay, just remember the basic things regarding forces and moments. Okay, just that. All right, so now you are going to bring in the legendary three-dimensional potato. Okay, so what is it? It is this. This is the legendary three-dimensional potato. All throughout our studies of solid mechanics, the higher and higher you go, you will have to deal with this three-dimensional potato. Okay, and even if you study fluid mechanics also, you'll have to deal with this. And the first part of this discussion, it has nothing to do with solid mechanics specifically, it has nothing to do with fluid mechanics specifically, it has everything to do with what is generally referred to as continuum mechanics. Okay. And the presentation will be not like Beer and Johnson. Okay, so first concept is traction. So we have this three-dimensional potato, and what we'll do is we'll take a cut through it. This color is not good enough. We'll take a cut through it. Now when we take a cut through it, it will divide it into two regions. This is the region 1. This is the region 2. for our purposes, we'll consider the region 1 and we'll separate it out. So maybe something like this. I'm just trying to redraw the region 2 as best as I can. Please accept that it is the same region, sorry, region 1. It is the same region 1. Now, this three-dimensional potato is being acted upon by a number of forces. Okay, and it is also supported properly so that there is no rigid body translation. So perhaps something like this. So we are going to have this same thing here. All the forces and everything are there. Now tell me, in this particular situation, is the region 1 in static equilibrium as I have drawn it? When it was here, this three-dimensional potato, it was in static equilibrium. Okay, but this is no longer in static equilibrium. What do I need to make it in static equilibrium? Internal forces. Okay, we need internal forces on this cuts exposed surface. On this exposed surface, I need to have the reaction forces from this region 2 on the region 1, or which is usually referred to as the internal forces. So I will represent them now. Very complicated distribution of internal forces. Okay. Now what I will do is, see, my intention here, let us not forget what the goal here is. The goal here is to arrive at a formal mathematical definition of this thing called traction. Okay. What I will do is, I will consider a little area within this exposed surface. Okay, I will consider a little area within this exposed surface. Now, within that area also, you may think that there is only one force coming out of it, but in reality, you understand that there are lots of forces and everything happening on that little area also. So, if I zoom into that little area, it will look like this. See, this is not this exposed surface, this is this little area. Okay, I'm just drawing it big so that it doesn't look cluttered. And here also, maybe if you, something like this, okay? So we have things like this. Okay, things like this. So there is a complicated distribution of forces on that little patch. And there is nothing special about that little area. You can take the little area here also, here also, here also, anywhere within that exposed surface. Now, what we'll say is that we are gradually going to shrink this area. This is very, very important. Okay. So I'm glad that I'm recording this, because everything that I'm saying now cannot be written, no matter how master a note taker you are. We are gradually going to shrink this. Okay. Now, when I shrink this, what do you think is going to happen? Well, the distribution of forces are going to become a little bit different. Okay. Right? Okay. Now think of it in another way. I have the little area. Now in that little area, suppose I consider the equivalent distribution of forces and moments. I have this very complicated distribution of forces. What will be the resultant? Just from directly from your basic engineering mechanics. There will be one force and there will be one couple. This is what you can do. If you have a number of forces from basic engineering mechanics, this much you know, that a complicated distribution of forces can be reduced to one force and one couple. This much is clear? Okay. Now what we'll do is we'll shrink the forces. We'll shrink the area. Now as you shrink the area, the distribution of forces will change. Everything will change. The forces will change. This resultant force will change. The couple will change. Okay. Now think in the limit, when I shrink this area so much that it practically becomes a zero area, then what is going to happen? It is not zero. It is tending towards zero. It is very important to make this distinction. Okay, it is tending towards zero, but it is not becoming zero. So when that happens, then this force, do you think it will become zero? Well, not necessarily. Okay, it may, but in the most general case, it need not become necessarily zero. But what about the couple? Couple will be zero or not? Why zero? Yes, very good, very good. So the answer is that in the limit that the area of this little region, it becomes zero, or it tends to zero, the resultant force will still have a finite value, but the couple will tend towards zero also. The reason is that this couple is actually what? It's a couple of forces, right? It's a couple of forces. There is a moment arm in between. That moment arm, as the region shrinks in area, that moment arm itself is becoming smaller and smaller. Okay? Because that moment arm is becoming smaller and smaller and is tending to zero, that is why the couple tends to zero. Okay? So we say like this formally, that as A tends to zero, you are going to have a finite value or a finite magnitude of this thing. Okay, but this couple, this is going to tend to zero. Fine. Now what we'll do is we will take the ratio of the force by the area in the limit that the area tends to zero. Now please understand that A tends to zero. Okay, A tends to zero. Here, this is, but it is not zero. Okay, it is not zero. This has a finite value still. Okay, this has a finite value still. Now, whatever the value of this thing is, that is what is referred to as the traction. That's it. So let that sink in. Okay. It sounds very interesting if we say things like that, Formula 1, tire grip and all those things. But ultimately, when you have to actually think about it in a mathematical fashion, this is what it is. Now, it is important to understand a few very, very crucial points regarding this. First of all, this A tends to zero, you have to actually qualify it. Because please note that if A really tends to zero, what is zero? Okay, so does it mean that we are going to a micron scale region, or does it mean that we are going to a nanometric scale region, or does it mean that we are going to an angstrom kind of region, or maybe subatomic kind of length scale? What are we talking about? Because if you are saying zero, then we should be really, I mean, what is zero, right? If it is tending to zero. So herein, whatever I discussed or whatever I have given you in the 0th chapter notes, that is going to be very, very important. It's not there. It's not there. It's there in the course website. So I have typed up one note, I think like 3-4 pages, and within that you will see there is a section called continuum hypothesis. Okay, so continuum hypothesis. So when we are doing solid mechanics or fluid mechanics at this at this scale, at the macroscopic scale, then we do not recognize the presence of atoms or molecules or subatomic particles, all those things. It is one continuous blob of matter. Okay, so it is in that sense that we are talking about the zero. So this zero is actually not a zero, it's a zero star. In certain books, this is written very clearly that this area is a zero star. That zero star means that it is zero, but at the length scale at which continuum hypothesis is still valid. Okay, none of these things are mentioned in your Beer and Johnson. Okay, all right. So this is our traction definition. Another very important thing to note, or couple of points to note, is that you see how the definition of traction is very, very, very restrictive. In the sense that what are we talking about here? This traction, first of all, we said that we have chosen a certain arbitrary region and then we have shrunk it to a point. Okay, we have shrunk it to a point means that area is tending to zero means shrunk it to a point, which means that the definition of traction is intrinsically connected to a certain choice of the point at which you are interested. Okay, it cannot be at any point. When you say the traction, it means that the traction at a certain point only, nothing else. Okay, the traction has to be at a certain point of interest, meaning that the value of the traction at this point and the value of the traction at this point and the value of the traction at this point are going to be completely different. Right? This much is very much clear. But there is another thing. Even before we chose this region and we shrunk it to a point, you have to understand that what we did, we took this bloody cutting plane. Right? What is the implication of taking this cutting plane? Implication of the cutting plane is that you are restricting yourself to a very unique outward normal. Okay, so when you cut this plane and you expose that surface, are you not saying that I am only interested in the unit outward normal which is projecting out like this? Because over this entire region there is a unique outward normal. No matter where you stand, there is a unique outward normal. Right? Okay, so the choice of this cutting plane is very, very important. So this traction, you note, it is not only connected to the distinctiveness of a point where you are concerned, it is also associated with the choice of the plane on which you are concerned, which is why this traction T is actually written very formally in this fashion, that this is a function of the point. This x vector represents the position vector of the point of interest. Furthermore, it is also associated with a very unique normal. I should not say very unique, it doesn't make any sense, it's a unique normal. Okay, so x as well as the normal. Both these things have to be defined. Yes?
So the plane is an arbitrary plane?
It is an arbitrary plane, but you have chosen something, right? You have chosen something. Okay. All right, so whenever you say traction, it means that at the back end, there is a choice of the plane involved, there is a choice of the point involved. Never ever forget this. Okay. Now, some of you may be thinking, oh man, in class 11 and 12, I thought that this was the stress. This is not the stress. Okay. Stress has something, of course, to do with traction. We'll see that, but it is not directly the traction, or it is directly not the stress. So what we'll do now is we'll again consider the three-dimensional potato. And now we are going to take a choice of our cutting plane in a very special manner. We'll take our cutting plane like this. What is so special about this cutting plane? It is parallel to the YZ plane, which means that if I expose the region 1, which is this is the region 1, then on that exposed surface, the outward normal will be parallel to the x-axis, right? So let me draw that. This is my exposed surface, and let's say that my traction vector uh, I don't like the colors, so maybe this. This is the traction vector at this point. Okay, this is the traction vector at this point, and the this is what? This is the n hat, and n hat is what? This is the I hat. Okay, I hope nothing should be unclear up to this point. Okay, if you're with me so far, now you tell me something. Can I now take the dot product of that t with the I? Okay, so t dotted with I. What is this thing? It is the component of the traction vector at my point of interest on the plane that I have chosen to take in the x direction. Okay, it is this mouthful. Okay, so this thing I will call, believe it or not, as this. Okay, so this is the sigma xx. This is the sigma xx. Now you tell me what should be the tau xy. T dot j. What is the txz? It is t dot k. Good. Yes.
Your definition of traction is saying that it is pointing towards from there bottom.
Yes, yes. Tell me.
That will say it has to be in the direction of the any bar.
No. I'm glad you raised this doubt. So please note that this traction vector is pointed along the direction of the f. It is not pointed along the direction of the unit outward normal. This f can be pointed along any direction. Okay, depending on the direction of the internal forces, the resultant, whatever the game is going on, it has no business being parallel to the unit outward normal, which is why here you please note that I've been very careful about writing this thing like this, that the t vector is not at all parallel to the n. Okay, in general it will never be parallel to the n. When it is parallel to the n, that will be the topic of discussion of another whole section. Okay, when it will be like that. So we'll cross that bridge when we come to it. It's a very, very important bridge. Now you see, I was being particularly choosy in taking my cutting plane here. I took it parallel to the YZ plane. It's a very special case. But in general, I can be like this. I can take it in any direction. Okay. So I will reconsider that diagram. So again and again, I'll have to draw this three-dimensional potato. So I will consider it again. And again, I will draw my x-axis, y-axis, z-axis. But now I'm going to take my cutting plane like before. Okay. Now I will draw explicitly the traction vector on that region at a certain point. So let's say that this is my traction vector and my unit outward normal is something like this. Now see, I can decompose this traction vector in two different ways. These are the absolute fundamentals. If you get this in your head, later on many of the intricate derivations that we are going to do, it will be much easier for you. Okay. So the decomposition of traction vector can be done in two ways. First of all, this is Tx I hat plus Ty j hat plus Tz k hat. Please do not confuse those Tx, Ty and Tz with these things. These are uniquely specified only and only when you have taken the cutting plane like this. But when you have taken an arbitrary cutting plane, then also you will have a traction vector. And that traction vector, being a vector, will have necessarily a x, y and z component. Okay, it will have x, y and z components. Those are those. These are separate things. Okay, do not confuse this with this. Next, the same traction vector, it can be decomposed into these two components, the TNN and the TNS. What is the TNN and the TNS? TNN, it is along the unit outward normal n hat. In fact, I can write this as n hat. Okay, instead of En, you write it as n hat only. So the TNN component of the traction vector T is along the n hat, and the TNS is along the ES. Now what is ES? It is along the surface, but along the surface there are infinite directions. Which one is it? So I hope you are understanding my question. I have written this as TNN n hat plus TNS ES. This ES hat, you understand that ES will be perpendicular to n hat. Okay, that much is clear. And if it is perpendicular to the n hat, it will be grazing along the surface. Which surface? This surface. But grazing along the surface and perpendicular to the n hat, you have infinite such ES. Which one is it? Yes. That ES is in the same plane that contains the T vector and the n hat. So this thing has to be absolutely clearly understood. That ES, yes, it is true that it is perpendicular to the n hat, but ES also lies in the same plane Clear? Please think about it. It is not that trivial, because if you have like any two arbitrary vectors, it's not necessary that they'll be contained in the same plane. right? If you have two arbitrary vectors, it's not necessary they'll be in the same plane, right? If you have two vectors like this, are they in the same plane? No. But what is special about it? They have a common terminus. Okay, they have a common terminus. That is why it is necessary that T and N will be necessarily contained in a plane, or you can identify a plane, a unique plane in which the T and the N will lie. Okay, it will be always there. Okay, so as long as you find that plane, you just have to mention that this ES will be in that plane. So it is something like this. The ES is here. Without that restriction, the ES could have been here. It could have been here. It could have been here. It could have been here. Okay. All right. How does it help us? Well, it doesn't help us now, but in the future, it is going to be really, really helpful. So everything, all of these things will be, I mean, please keep on writing it down with me.
So
Yes.
this point where you are considering the traction vector, is that the center of like
Absolutely not. It can be any point. Any.
sigma x that different?
Absolutely. So the question which you want to ask, I believe, is this: that if I take this point, and if I'm claiming that there is a traction vector which is like this, and if I take another point, there will be another traction vector. Then, if the components of that traction vector are these, then for the other one, it has to be something else. Yes. So each and every point you take, there will be different sets of these sigma xx, tau xy, tau xz, which is why it is extremely important to identify, recognize and respect that when you take a three-dimensional body or a two-dimensional body and you take a cut and you expose that surface and you look at different points, different points will have different conditions of states or stress. That is referred to as the state of stress. Okay. Actually, you have encountered this. You didn't recognize this probably. See, when you are doing bending, sigma is equal to minus my by I. On that surface or on the cross section, do you not have different values of the sigma? What is that? Okay, so all those sigmas, the sigma x is different values, they happen to be the components, the x components of certain traction vectors. Similarly, for shear stresses, when you consider the shear stresses which are generated in response to a torque-like situation, the torsion chapter, there you have the tau is equal to TR by J. Do you not have that? Now, if you take different values of the radii on the same cross section, do you not have different values of the shear stress? So does it not make sense that on the same cross section you can have different values of the shear stress? It is absolutely possible. Not only is it possible, that is the general thing. Okay. Yes.
But that example we saw that as area tends to zero, the moment.
Sorry.
The movement should be zero, right?
Right. Yeah.
But here, if you take a moment about the, let's say, the center of that plane, exposed plane.
No. Not that moment. It has to be the moment within that area. Because when you are doing this thing, your entire universe has shrunk to this. Then don't worry about the rest of it. This is the general distribution of forces you have. Okay. So the axis has to be within it. Okay. We are only prepping ourselves for future big and great things. Okay. So one of the first big things that we are going to consider is what is referred to as the Cauchy's theorem. Okay, the same Cauchy. Okay, which we have encountered in maths, the same Cauchy. So it is the Cauchy's theorem. It basically gives us a very general connection between the traction vector and the sigma. The problem with Cauchy and Euler is that they have so many theorems and so many things associated with them. Which one is what, you have to make out from the context. Euler's theorem has no meaning. Okay. Similarly, Cauchy's law and Cauchy's theorem, God knows what are you talking about. So from the context, you have to figure out. So this Cauchy's theorem will be the one which is connecting the traction vector with the stresses. But before we reach that theorem, very, very important theorem, we have to, wade through quite a bit of geometry and very important things. We'll do that. So, so let us take our mind back to maybe BEM. You consider this diagram again. Okay. So everyone, please look at it. You consider this diagram again. We took a cutting plane which is parallel to the YZ plane. We exposed a surface which was perpendicular to the I hat, and we got these three components, sigma xx, tau xy, and tau xz. But suppose instead of taking a cutting plane which is parallel to the YZ plane, we had taken a cutting plane which is parallel to the XZ plane, and we ended up exposing a surface which was on which the unit outward normal was along the y axis. Then what would have happened? Huh? I'm going to point out something very, very special here. See, we have considered this point, right? Okay. This point has an existence in this original three-dimensional potato. Okay. Let's say that this is here. This is this diagram. Okay. This is the point here. This is the same point here. This is the same thing. Okay. Now, this point is very much contained in this cutting plane. But now, suppose I take this horizontal cut, and I take the horizontal cut in such a fashion that it passes through that very same point. Okay, it passes through the very same point. Now the region exposed will be different, the unit outward normal will be different, but the point is the same. Do you think on that exposed surface the traction vector will be the same vector as this t? It's not a trick question, just think of it conceptually. It is going to be absolutely different because the choice of the cutting plane has now become different. I told you right earlier, the t vector has to be uniquely specified on the basis of two things: the choice of the point in which you are interested, but also the cutting plane on which you are interested. Okay, because the n hat has now changed, the t vector completely changes. Okay, all right. So that will be a different thing. Again, if you take a cutting plane which is parallel to the xy plane and you expose a surface on which the unit outward normal is along the z axis, then also you are going to get a traction vector which is going to be different. Okay, and then also you can take these different components. Okay, so I'm going to make a connection with this diagram that I had drawn earlier, and I'm going to write something like this, that it will be completely different vector. It just happens to be located at the same point. So see, this picture will be something like this now. Is it not? This is going to be the picture. You are going to have a traction vector which is like this, maybe somewhere. Please note, I have written the same t vector, but if you are really very careful, you may write something like t j hat or something like that, or the superscript, or t2 or something like that. Okay, just to distinguish it. It is not the same t as that. And now, if you take for this t vector different components, what are you going to get? For this t hat dot I, what is the stress component that we are going to get? Tau yx. If you take t with j, what are you going to get? Sigma yy. Very good. What is it? Be careful. Tau yz. The distinctive feature here is that the first superscript, first subscript is y. Okay, denoting that you are considering a plane on which the outward normal is along the y direction. Okay. Again, wait. Let me finish this. For cutting plane parallel to the xy plane, you are going to have something which is very difficult to draw, but I'll try nonetheless. Okay, so it is going into the plane of the board, okay, something like that. So here you are going to have a traction vector which is just projecting out of this thing. Maybe by the time you send your kids to IITs, they will have three-dimensional boards or some holographic features or something. Till that day, we are restricted to this two-dimensional surface and have to make the best use of it. Okay, now you tell me very quickly. T dotted with I. What is it? Tau Zx. Very good. Tau Zx. T dotted with J. Tau Zy. Very good. And T dotted with K. This is sigma ZZ. Right. So see, now we have managed to expose ourselves to the full glory of the three-dimensional thing, where we have all these 9 different components of stresses. Okay, 9 different components of stresses, and what we are going to write down is we'll arrange them in a matrix. Everyone, please be very, very careful when you are writing down the subscripts. Please do not write the tau yx here. It makes a world of difference. Later on, tau xy may be equal to tau yx. But in terms of our conceptual understanding, we should not hide behind the mathematics. Okay? This is what? This is nothing. Okay, this is nothing. We have it just so happens that we have managed to find out 9 different entities. These happen to be the components of the traction vector. Okay, we have 9 entities, and we know that in a 3 into 3 matrix also we'll be able to arrange 9 elements. That is why, as a mathematical convenience, we have arranged it like that. One good thing about this arrangement is that in the first row you have all the components of the stress which are corresponding to the cut parallel to the yz plane, and then for the other 2 planes also you have those things. It is just a matter of organizing the things in a clean mathematical fashion. Okay, but there is a deep connection within the maths also. So this thing is what we'll refer to as the stress matrix. Okay, we'll call this as the stress matrix. Everyone, since you are my students, all of you, religiously, okay, put 2 tildes beneath it. Not 1 tilde, not 3 tildes, not above it, not sideways. Beneath it you put 2 tildes. Okay, later on you will thank me. Okay, so this is the stress matrix, but you put something like this also. So what we are saying here is as follows. This sigma is the stress. The two tildes beneath it represent that it is the second order tensor. Okay, don't worry about tensors right now. And this matrix or this box around it, it represents the square brackets around it, it represents that this is not the tensor. This is the matrix representation of the tensor. Okay? I am not mad. Okay. Now that we have all of these things, we are kind of ready to start the chapter properly. Okay. All this while, we were just preparing ourselves for what we have to actually study. So, I'm not leaving you. I given you break, you stayed with me. What we'll do now is to take the first steps uh, towards the derivation of the Cauchy's theorem or the Cauchy's law. Okay. So, one thing which we have to identify very clearly is this. All of these things that we have done, all of these things that we have done, all this arrangement into the stress matrix and everything, we want to see geometrically where is it, how is it. Okay. So this time, for a change, we are not going to draw our three-dimensional potato. Okay. So when we were talking about this sigma xx, tau xy and tau xz, which plane we were considering? We were considering a plane which was parallel to the YZ plane. Very good, YZ plane. I am going to draw because I have different colored chalks. I will draw these things in separate colors. Okay. Let's say that this is our. So since you guys don't have the luxury of different colors, maybe you can do something that you draw these things in different styles. Maybe something like this, okay. Okay, the other one completely connected, the other one like dot dot dot, something like that. This diagram is going to become horribly messy. Okay, I promise you from before. So this is the plane parallel to the YZ plane, and when you take the traction vectors, you get all this sigma xx, all these things. Okay, now we are going to consider the plane parallel to the xz plane. What is that? It is this. And finally, there is a plane which is parallel to the xy plane, which is this. Okay. Now see, they are cutting at a single point. Okay, they're cutting at a single point. That point is here, let's say. Okay. Now on that point, you are getting the different traction vectors. So all these things that we have separately considered, this is that same thing. Okay, superimposed on one another. So here the traction vector was like this on this red colored cutting plane. On that thing it was like this. Then on this thing it was like this. Okay, fine. This is the real picture. So now you see that if I have to take not just, or if I have to draw not just these traction vectors, so this was the traction vector, this was another traction vector, this was another traction vector. Okay, this one was corresponding to the x direction, this was for the y direction, this is for the z direction. Now, on top of that, if I have to draw its components of this one are what? Sigma xx, tau xy and tau xz. For this one was tau yx, tau sigma yy and tau yz, and for this one was tau zx, tau zy and sigma zz. In this same diagram, if I have to draw everything, how much more messy it is going to become? Right? Is it not? All agreed? Okay. Recognizing this fact that it is becoming very, very cluttered and it's extremely difficult to understand, what people do is as follows. And they never tell us. Okay. They draw this. What is this? This, the unsaid claim or the unsaid explanation is this, that there is a point inside it. Okay. And beside that point, you have taken two parallel planes which are very, very close to that point. And which are very, very close to that point, which are very, very close to that point. These two pairs, these two pairs, these two pairs, like this. Okay. And those two pairs, in reality, they represent the same plane. It is just that you have to spread it out. So if you take this cutting plane and you just spread it out a little bit, okay. If you just spread it out a little bit, it is those two things. So this is the red colored thing. This is the green colored thing. This is the yellow color, all these things, okay. But it is ultimately the same thing. So it is only at the same point that we are considering. And that is why after drawing this, they write it very beautifully like this. That here you have sigma xx Not only this, if you take the other hidden planes, on those also you will have their brothers and sisters. Okay. But what they don't tell us is that it is actually at the same point only. Okay. So this is a big, big confusion which has been propagated since time immemorial. Okay. But actually it is this diagram, this horrible, horrible, messy diagram. Okay. Now, what we'll do is, we will not consider that clean diagram. We'll consider this horrible diagram only. Okay, not because we like to torture ourselves, but because the Cauchy's theorem will come out very nicely out of it. And because I have practically run out of time, the one thing that I'm going to draw is that, see here, maybe I draw this thing. This is the x-axis, this is the y, and this is my z. Now I am going to draw another plane because 3 was not enough. Okay, I am going to draw another plane which is arbitrary. Okay, so which plane is this? This is the arbitrary plane that I have shown you on the cutting plane. Okay, and please note, the special thing about this cutting plane is that this too also passes through that point. Okay, the motivation here is this, that I am going to connect all these different traction vectors. Okay, because you see, the moment I take a cutting plane and I have that same point in which I am interested, I'll have another traction vector here also. That traction vector will be connected to all these other things. Okay, so that's it. Thank you.